So today topic is topicity. So this is one of the important topic in stereochemistry. So there we have three types. The first one is homotopic ligands and phases. The second one is enantiotopic ligands and phases. The next one is diastereotopic ligands and phases. So out of means these all three are very important. The first we'll talk about the homotopic ligands and phases. So this is very simple to identify. So the molecule which is given if we have a center of inversion, plane of symmetry, or this chiral point groups, any molecule having these point groups, they will not belongs to homotopic. Only molecules which show CN axis of symmetry, they only become a homotopic ligands. So how you will say homotopic and ligands and phases? So we'll take a dichloromethane, Cl and hydrogen. So this is A and B. Now we replace this Ha by deuterium. So we'll get Hb, Cl and D. And now we replace Hb with deuterium. Then we get this compound. So these two compounds are same. So here first of all there is no chiral center. So because of that reason these two compounds are same. So because of that these two hydrogens in dichloromethane are what we say homotopic ligands. Okay, and then when we take a cyclohexane, so here we need to see about the temperature condition also. So when we'll take hydrogen, axial hydrogens and equatorial hydrogen, definitely they are not homotopic at low temperature, but at room temperature and at high temperature what will happens, there is a interaction between the axial and equatorial positions. So because of that reason at high temperature all the hydrogens of cyclohexane are homotopic in nature. Okay, next we can also take this system, tartaric acid, H, OH, H and OH. So when they ask this kind of hydrogens, so we have to go for the R and S nomenclature so that it will be very easy to identify. So here they are asking that what is the relationship between these two hydrogens. So first we replace this hydrogen, this A hydrogen, this B hydrogen by deuterium, so that we'll get deuterium OH, CO2H, OH and H, CO2H, and we'll give the RS nomenclature here. So this will be 1, then 2, 3, 4. This is R, and 1, 2, 3, 4, and this also R. This is 2R, 3R, and after replacing one hydrogen with deuterium, so now we'll give the numbering here. So here also almost it comes same. So this is 2, this is 3. So here this is a 3R because no change, and here 1, 2, 3, 4, and here also 2R. So after exchanging with deuterium, this is showing same. And now we talk about HB. For HB also CO2H, OH, 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 deuterium, CO2H. So this is 2R, and here 1, 2, 3, 4, and then like this this is 3R. So these two hydrogens, these hydrogens are homotopic in nature. So one thing here we need to remember, if these two hydrogens are homotopic, then these two hydroxyl groups are also homotopic. So in this compound, two carboxylic acids, two hydrogens, two OH, all are homotopic in nature. So even if you replace this carboxylic acid with some other group, so you will get same RS nomenclature. Okay, so this we have to remember. This is 1, 2, 3. Okay, now this is about the homotopic compound. So any compound is given like if there is no, and this one if this is tartaric acid, if they ask mesotartaric acid, if you replace this hydrogen with some other group, so here we will get enantiotopic relationship. Okay, when we are taking this dextroliver compound, in case of dextroliver compound, the hydrogens are homotopic in nature. In case of meso compound, it's a enantiotopic in nature. You can try for this also, so you'll get enantiotopic. So this is about the ligands. So what is the phase? Phase means any, like here. Okay, here also, like if two ligands are same, then it comes under homotopic phase. If two ligands are different, for example, we take what is this, acetaldehyde, so this will comes under heterotopic phase. Okay, so where if we replace okay, I will explain in another paper. So here we have acetone. Now we are doing a Grignard reaction. So here two possibilities are there. The methyl group can go from the above the plane or below the plane. Okay, one product is methyl group went below the plane. So another product, in that case methyl is above the plane. So these two are, we can't distinguish. So these two are same. So when these two groups are same, that time we call this as a homotopic phase. When this is different, that time we call as a heterotopic phase. Even when we have a this compound, so this also we call it as a homotopic phase only, because this is not chiral in nature. So if it is a chiral, I mean like alene systems, if it is like this, so this we call it as a homotopic ligands. Okay, even I mean this is below the plane and this is above the plane, we call this one as a homotopic ligands. But when we have a chiral center here, a hydrogen and methyl group, and here we have hydrogen and hydrogen, so we cannot call this one as a homotopic ligands. So just remember what is homotopic and what is a homotopic ligands and what is homotopic phases. So these are, now I'm telling small things only, but I will make one more video, that in that video I will be discussing important problems also. So this is about the homotopic phases. So now the next one is a diastereotopic phase. Diastereotopic ligands. So this is very important, diastereotopic ligands. So in examination point of view, diastereotopic ligands are very important, and as well as enantiotopic also. So We know that what is diastereomers. Diastereomers means it will not show any kind of symmetry. Okay, there is no symmetry. Generally, this topicity we identify by two ways. The first one is substitution or addition. So like what I have done before. So this is a substitution. Okay, now like symmetry, next method is a symmetry criteria, on basis of symmetry criteria. So I have said before, actually for homotopic ligands they should possess CN-axis of symmetry. If they are possessing CN-axis of symmetry, then it comes under homotopic ligand. If they are showing plane of symmetry, center of inversion and chiral point groups and D alpha H also, so these all comes under the enantiotopic and diastereotopic. Okay, so just remember, I will tell only one thing here for diastereotopic. Like uh, any hydrogens which are adjacent to the chiral center, so those are a diastereotopic, because we know that where we have chiral center, there we will not see any kind of symmetry except C1 symmetry, right? So diastereomers means what? There should not be any kind of symmetry elements in for diastereomers. That's why, so where we have hydrogens adjacent to the chiral center, they are a diastereotopic in nature. And then these alkenes, HB, HA, H and methyl, and these two are diastereotopic in nature. And then, so this kind of problems are very very important. Here we have HA, HB, then Br, hydrogen and Br. Okay, I have so many problems like this in these compounds. So I will be making one separate video only for problems for diastereotopic, enantiotopic and homotopic. As of now, I'm trying to explain what is a diastereotopic, what is enantiotopic, and what is a homotopic. And these two hydrogens will be diastereotopic, because if we replace these two hydrogens with by the some other group, so we can't means like it will not show any kind of symmetry. Imagine that here I took some chlorine group, this is HB, and also this is HA, chlorine, bromine and hydrogen, here hydrogen and bromine. So we can't apply any kind of symmetry elements here. So because of that reason it comes under diastereotopic. But when this hydrogen and this hydrogen, if we see, so just remember that I will tell one example here. So we know that like there is a one simple thing to remember: 1 2 3 4. So this is the chiral center. It's having 4 different groups. Now what will happen if we do the mutual exchange of 90 degrees, any two groups mutual exchange, that is called as enantiomers. If we do mutual exchange of 3 groups, any 3 groups, then it forms identical compounds. Okay, so it should like I will take one example here for an enantiotopic. It's like let me think. We have a cyclopropane system, then here this hydrogen, uh, wait, H, and here OH we have, and here methyl and H. Okay, so now I am writing another structure. So in this structure what I am doing, sorry, in this structure what I am doing, no wait, here we have methyl and hydrogen and OH, and in another structure OH, hydrogen, methyl and hydrogen. And the question is, the molecules among the following are belongs to constitutional isomers, enantiomers, diastereomers, identical. So these are the options. So when they ask this kind of questions, so it will be difficult. Like you can give RS nomenclature, like we'll try for that. 1 2 3 4, and this is R, and here this will be 1, and then this will be 2 3 4, and this is S, and here 1 2 3 4, and this is R, and then 1 2 3 4, and this will be S. Okay, so here this carbon is having a R configuration, and this carbon also having a R configuration. Okay, and this carbon is having S configuration, and this carbon is having a S configuration. So what we will think, this is belongs to enantiomers or constitutional. So it can be possible for constitutional isomers or enantiomers. So it cannot be a diastereomers, because we can apply some symmetry element here, like when we have like this, we can pass a plane like this, so that we can apply the symmetry. So it cannot be diastereomers, or it can be identical, because RS and RS is there. So these three are the options. Okay, so just remember, as I said, that if there is a two groups are undergoing a mutual exchange, okay, so if it undergoes a mutual exchange, that comes under the enantiomers. Okay, and here like this is 1 2 3 4, this is R, and then this should be 1, this should be 2, this should be 3. Yes, okay, and here this should be 1, this should be 2 3 R. Okay, so as I said that sometimes this RS nomenclature may not help. Like for these compounds I prefer this way, like if the mutual exchange of 90 groups 90 degrees is there, then I go for enantiomers. And there is another important one I want to explain here before going for enantiomer topic, that is the constitutional isomers. So what are the constitutional isomers? So constitutional isomer means same molecular formula but different connectivity will be there. Different connectivity, like this compound. So here fluorine and hydrogen. In other compound we have a fluorine and hydrogen, fluorine and hydrogens. So here we have same molecular formula, but connectivity is different. Connectivity means here two fluorines are attached to only one carbon, and here two hydrogens are attached to one carbon. But in this case, one fluorine, one hydrogen, one fluorine, one hydrogen. So this is called constitutional isomers. So in examination point of view, this option will be there. Definitely this option will be there. If they are asking about topicity, definitely constitutional isomer option will be there. And if you know what is the constitutional isomers, you can easily remove these options, and you left with three options. You can apply the elimination method for these compounds. You can apply elimination methods. First see the conductivity is same or different. If it is the same, then it cannot be constitutional isomers. You can eliminate this one, and then go for symmetry. If any symmetry is there, then you can remove the diastereomers, and the answer will be either enantiotopic or diastereotopic. And we can also see the mirror image relationship like this. Okay, and this is below the plane, this is below the plane, below here, and here is above. So it can also be a mirror plane. Okay, so if you are answering for this kind of questions, means you should confirm it by more than one way. So you just remember this one. So this will helps, and shortcut way, this is a shortcut way, you can easily identify it. So that is about the diastereotopic. And then diastereotopic phase means here we don't have any kind of symmetry in this case. Okay, we have only a plane of symmetry will be there if you plus a plane like this. Okay, just remember all exo and endo comes under the diastereotopic. Cis and trans also, because cis and trans are they are diastereomers, exo and endo also diastereomers. So this way you can remember. So it's very easy to identify the diastereotopic ligands and phases. I will be explaining examples tomorrow, but just remember, if no symmetry means that is a diastereotopic, and the one which is adjacent to the chiral center, that also diastereotopic. And next what is left is enantiotopic. Enantiotopic. So here if you are writing for enantiotopic, like there should be a plane of symmetry. I can take COOH, methyl, this is HA and HB. So first we replace HA, some chlorine will take, COOH, methyl, HB, and here the RS nomenclature is perfect. When we have this kind of systems, the RS nomenclature is perfect to identify whether it is a enantiotopic or diastereotopic. 1 2 3 4, this is S, 1 2 3 4, and this is R. So S and R is enantiomers, R and R, S and S is enantiomers, R and S and R are enantiomers. You just remember this one. Okay, this relationship you just remember. So this is about the, I am not going details into the enantiotopic ligands and phases, because I am going to explain I am going to solve the problems, so there we will come to know. And what are the conditions for these chiral ligands? The first condition is the molecule should have sigma plane, and the molecules like CI, which is having center of inversion, and then like molecules which belongs to C alpha V and C alpha H. I mean, not all molecules, this is only for achiral molecules which are having this kind of symmetry elements, so there it will exist. So I will be explaining your problems in the next class. So this is just a basic idea. I'm just giving how to identify homotopic and diastereotopic and constitutional isomers. So once if we solve the problems, then it will be easy. Okay, I will some few problems I will solve now, so that it will be easy. So here we have this question. I hope it's not it's not visible, so that's why I'm writing here. H methyl, H and fluorine, CH3 and H, F and H. So this is very easy to identify whether it is enantiomers or diastereomers, because it's just like a mutual exchange. This goes here and this comes here. So anywhere the mutual exchange is there, that comes under the enantiomers. Okay, and this problem, the molecule below is belongs to constitutional isomers, enantiomers, diastereomers, identical, and stereoisomers. So I have explained this one before also. So here we have fluorine for same carbon, and in the second structure we have a hydrogen fluorine and hydrogen fluorine. So the same molecular formula but connectivity is different. So this is comes under the constitutional isomers. And this one here will take 12th one. This also I have done already. And here we can see we have a cyclobutane, H and F, and then we have a H and F. So the options what he is given is constitutional isomers, enantiomers, diastereomers, identical, and none of the above. So it cannot be enantiomers because they have 4 carbon, here 3 carbon. It cannot be diastereomers also, it cannot be identical also. It cannot be constitutional isomers also, because here 4 carbons are there, only 3 carbons are there. So this comes under none of the above. And this one, methyl and hydrogen and methyl, now hydrogen, methyl, hydrogen and methyl. So these two, what about these two? See, one thing here, if you don't know anything also, you can easily solve this question, because like if you see this hydrogen and methyl, this carbon is fixed, only this carbon is shifted. Okay, I said that the mutual exchange, there should be a mutual exchange. If mutual exchange is there, then that is enantiomers. Since it's no mutual exchange, we can remove the enantiomers. And if a 3 carbon is, so here there is no mutual exchange, so we can remove the enantiomers. And it cannot be identical also, because only identical means 3 groups has to be shipped, 1 2 3 4. So we can keep one group constantly, 1 is coming here, 2 is coming here, and 3 is going here. So this leaves identical, but here only 1 is shifting. So you can close your eyes and pick a diastereomers option. It's that simple. You just need to remember mutual exchange and 3 exchange when they ask this kind of questions. And when they ask for this kind of questions also, you can use this method. And when they will ask imagine that they ask this kind of question like lithium aluminum hydride, so that time we have to follow Cram's rule and other things. So I have this kind of problems also, I will be explaining it. First we will see small things, so that you will be having some idea, then we will go for big things. And next so we'll take this 18th problem. Here we have hydrogen and fluorine, we have methyl and fluorine. So here we have a constitutional isomers, enantiomers, diastereomers, identical, and none of the above. So I have explained what is the constitutional isomers. The same molecular formula but different connectivity. So here we have same molecular formula but different connectivity, because one CH2 is not here, but we have a methyl group. So this comes under the constitutional isomers. And then here we have hydrogen and methyl, hydrogen and chlorine. Then we have chlorine and hydrogen, hydrogen and methyl group. So here also we can see the mutual exchange. So this comes here and this went here. So this will comes under the enantiomers.